In this video, we will be starting our series on pedigree analysis. Technically, this is still part of the course on genetics, but it's somehow its own story within the course of within genetics as a science subject itself. So I have to be honest with you, I am going to skip these. Let's start first with this worksheet over here. This, by the way, is from the internet. I'll be using it to teach. So a family tree of sorts is called a pedigree. So we have the following symbols that we'd like to know. A circle refers to a female. Actually, all circles. But if there's no shade, then it's an unaffected female. If there's a shade, then it's an affected female. For males, for boys, and basically men, the shape would be a square. And if it's unaffected, there's no shade. If the male is affected, then there is a shade. So, yeah, other things to note. We have siblings are placed in birth order from left to right and are labeled with Arabic numerals. Each generation is labeled with a Roman numeral. Therefore, the male exhibiting the trait in the pedigree below in the bottom center will be identified as 3, 4. Okay, so this is generation 3, and the male exhibiting the trait. Is it this? I think there's something wrong with this. With the instructions. This is supposed to be female because again, the circle is supposed to be circle. The circle is supposed to refer to females, not males. Kinda sus. Anyways, let's answer number 1. I'll just copy paste the questions. I already have the flow chart, this entire thing. I did write it down before I started this video, so it could save a lot more time. Okay, so how do we start this? I actually don't remember clearly, but yeah, let's give this a try. Number 1, which members of the family are affected by Huntington's disease? By the way, Huntington's disease, what is it again? Okay, so this is also important to note. Okay, so for the first generation, I believe these are the grandparents, these are the parents, and these are the children. Generation 1, generation 2, generation 3. So the father, the grandfather is affected. What is Huntington's disease in the first place? It's recognized to be an autosomal dominant disease. So although it's not stated directly in the instructions that Huntington's disease is dominant, it's important to note, like, if they mention Huntington's disease, then it's already implied that it's dominant. You just have to memorize it before taking on exams related to disease. So yeah, Huntington's disease dominant. What next? Okay, I believe question 1 is very simple. So which are affected by Huntington's disease in the entire bloodline? Basically, you just want to look for all of the shapes that have a shade. So we have 1, 2, 3, 4, 5. So we have 5 people affected by this Huntington's disease. How about number 2? There are no carriers for Huntington's disease. Either you have it or you don't. I believe that's the reason why it kind of makes sense, because this disease is dominant. If a disease or a trait is recessive, then it is already given that females can be carriers. In the previous video, I mentioned that females can be carriers in the event that uh, an X-linked recessive inheritance is involved. In other words, for example, this is a female, right? Two pairs of chromosomes, XX, for the sex chromosomes. And one of the genes, the genes in one chromosome is mutated. But even so, this is technically still a carrier. The female is unaffected, but she, not he, she is a carrier. If the disease or trait is dominant, then this same illustration or scenario for a female would mean that the female is affected. So yes, just to recall from what was mentioned in the previous vid. So yeah, either you have it or you don't. It's a sign that this disease is dominant. With this in mind, is Huntington's disease caused by a dominant or recessive trait? Okay, so I think you already know the answer. I just said it. This is caused by a dominant trait. Because in a dominant trait, for females, there are no carriers. But regardless, if a trait is dominant or recessive, a male will always only be either affected or unaffected. Males cannot be carriers because they are XY. For females, they can be carriers in a recessive trait because they are XX. There are two X chromosomes, like literally. So, yeah. Granted, okay, I'm not gonna say anything anymore. Number 2, is it correct? Yes. So far so good. We have the same answers as the answer key. How about number 3? How many children did individuals I1 and I2 have? How many children? So I think what's being referred to are these two individuals, the grandparents, I1 and I2. We're reading from left to right, just like how we read in English. Not in Chinese where we read from right to left. So this is I1, this is I2. So how many children did they have? Let's count. 1, 2, 3, 4. Wait, sorry. Whoops. Too much haste. We only count the children, not the suitors of those children. So be careful. So this is the link. So we have 1, 2, 3, 4, 5, 6. 6 children. This and this, both of them are not considered children. They're suitors. As you can see, there's no line connecting them. So 6 children, I suppose. Is it correct? Yes. How about number 4? How many girls did Generation 1 and Generation 2 have? Sorry. Both in Generation 2, 1 and 2. How many children did they have? 3. Sorry. How many girls, not children? Girls are more specific. So we want to count how many circles there are. So we have 2. So 2 girls. Regardless whether either one of them or both of them are either affected or unaffected, there are still 2 girls nevertheless. And yeah, if the question asks how many children they have, then it's obviously 3. If it asks how many boy children are there coming from these 2 individuals, there's 1. If what's being asked is how many girls are affected who are also children of these 2 individuals, then this is what we only have 1. If they say unaffected, then we say 1 as well. So that's it. How about number 5? How are individuals Generation 3 and Generation 3 2? Where is that? Generation 3 2 and Generation 2 4. So how are these 2 related? uncle niece relationship, I suppose, because this is a male. This male is siblings with an affected female, which is the mother of this unaffected female daughter. So instead of daughter, niece and uncle. Niece and uncle. Ah, okay. Maybe aside from what's generic to understand, even if you didn't study genetics, it's understandable that you can say the answer that I just said, a nephew and sorry, a niece and uncle relationship, but the answer in the context of genetics is that basically they're related in the sense that both of them are not affected by Huntington's disease. So that I think that makes more sense. What was I thinking? Okay, so that's it for number 1. So that's basically how we analyze pedigree, what do you call this? Flowcharts? Z's, I mean, not this, plural. Let's go to number 2. So we have 4 generations total. And yeah, it's drawn again here. I suppose I'll just let go of that. You know what? I'm sorry, I don't trust my own work. I don't trust my own copy. I'll just copy from the actual worksheet itself. Have this thing shrinked. As laggy as my iPad already is, I'm trying to be as economical as possible. An iPad Air can only do so much in making a world of digital notes for a student, especially that I'm going to college in a few months. Okay, this is number 2. What's her question? The pedigree above shows the passing on of color blindness. Okay, color blindness. Okay. I'm not sure if color blindness is dominant or recessive. But based on the next question, based on what followed the statement of question number 12, its carriers are mentioned. So possibly it could be implied that color blindness is a recessive trait. Can we confirm that? Let's wait. Color blindness, right? Okay. Is color blindness recessive? Yes, a rare autosomal recessive trait. I think autosomal is associated with this idea, right? We have 23 chromosomal pairs, and 22 of them are under the category of autosomal, and the remaining 1 pair goes to the sex chromosomes. What defines the egg and sperm for female and male respectively. But yeah, autosomal. Anyways, we got our inquiry correctly. Oops, wait. Sorry about that. So we have a recessive trait, right? What sex is most likely to be carriers of color blindness? Well, this is, even if you don't analyze anything from this pedigree diagram, it's already given based on what I said earlier. Um, in a recessive trait, there are carriers. What sex are most likely to be carriers, regardless of the trait, as long as it's classified as recessive and possibly also autosomal as well? Only females. Males cannot be carriers. Let's see if this is correct. Number 12. Yeah, female, or the symbol for female. How about number 13? Why does individual generation 4, 7? So 1, 2, 3, 4, 5, 6, 7. Why does this female have color blindness? So number 13, it says the mother is a carrier and the father is affected. Okay. Sure, let's try that out. Um, since the mother is a carrier, let's say so we know that blindness is a recessive trait. So B goes for blindness, and capital B is normal. If a female is a carrier, then it's a heterozygous, both a capital and a small at the same time. For blind or affected individuals, they have homozygous small b, small b. Let's try out a Punnett square. So B, 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 B. It makes sense. Hang on, hang on. I forgot to put the sexes. So this one is female, right? And the small letter B's are for males. So what's the outcome? Okay, so we have 50% of the offsprings affected. We're talking about the phenotype. And 50% are heterozygous. This is gonna be challenging. But yeah, we're able to find a block that's missing. So we know that 50% are affected. It's basically these two guys. I mean, one affected male, one affected female. And these two are, I think they represent these. So for the female, since colorblindness is a recessive trait, for females, they become carriers, which is this. And for males, because colorblindness is recessive, they are not affected. So technically, it's still a box without a shade. But granted that this, the scenario here is basically colorblindness. Let's say theoretically, they are a dominant trait. It's a dominant trait. Then this square right here will be shaded. But that's not the case because again, colorblindness is recessive. So yeah. Based on that Punnett square that we did, that we constructed, we could say that what possibly caused a female to have color blindness is because because the father is affected and the mother is a carrier. So yeah, basically granted that an affected father and a carrier mother get 4 children, or produce four children, one of them, 25%, there's a 25% chance of um, having a daughter who is affected. And yeah, that's the explanation for number 13. This is also the same reason for granted that an offspring is a male affected or a male unaffected or possibly a female a carrier at the same time, but technically still unaffected, just a carrier. Okay, number 14. Why do all daughters in generation 2 carry the colorblind gene? Okay, so yeah, it makes sense. All of the circles carry the colorblind gene. They're all carriers. They're not affected, but they're carriers. That's everything that we have to know. It has to do something with the parents. So we have a male, the grandfather who is affected, but technically it's recessive, so small b. The grandmother is normal, so possibly just BB. Not not this, because she is not a carrier. A carrier is symbolized to have like a circle, but it's like a half moon basically. But that's not the case for grandmother. So what could possibly be the offsprings? So let's try a Punnett square again. Oops. Okay, this is female, this is male. Okay. So 100% all offspring basically for males, they are not affected. But if there are females, then they're all carriers. So that's what this means based on the findings in our Punnett square. So all of the offspring are heterozygous, but their characteristics are different depending on their sex. So if for the males, all of the male offsprings will not be affected by the recessive trait, which is colorblindness. However, for females, they will also not be affected, but they'll be carriers, and they'll be bringing that gene. Um, they'll be the reason why some of their offsprings will be affected. Some of their offsprings will carry the gene that their parents once carried, particularly the father, or basically the grandfather of who will be affected. Okay. So yeah, I think that's the reason why we have that in number 14. Again, the father is affected. Mother is normal. So that's an instrument for, yeah, you know the rest. Okay, what does the answer key say? Affected father plus unaffected mother? Yeah, we just said the same thing. How about number 15? List 2 first generation colorblind males. So we're looking at this generation. Colorblind males, I'm looking at 1 and 5. So generation 4, person 1, and generation 4, person 5. Okay, that's it for number 15. Let's move on to number 3. Another reason why I'm enthusiastic about teaching this to you right now, even though it's been a few weeks already since I took the quarter exams. I did enjoy pedigree analysis. I wasn't able to catch up with my friends, with my peers. They were able to understand this lesson when it was already taught in the classroom. I'm a slow learner in certain cases, and this is one of them. Okay, back to number three. Is this trait dominant or recessive? Okay, so we're not given any idea regarding what this trait is. We don't know if it's dominant or recessive, but we need to justify given the details that are provided. Again, I don't trust my own drawing. It's been a waste. Okay. Um, is this trait dominant or recessive? So let's start here. Wait. First things first. In the entire diagram, there are no um symbols of half moon. So technically, there are no carriers in this scenario. So I think from there, it could be said that the trait is dominant. Because there are no carrier females. I hope the reason is valid. What's the answer? Okay, it says recessive. For what reason? All generation 2 people did not inherit the trait at all. Did not inherit the trait at all. Makes sense. Because usually, if the trait is recessive, then not many are affected. And it's perfectly reflected in what happened in generation 2. No one was affected. Yeah, knew it. My reason is too shallow. But the policy remains the same. In a recessive trait, female carriers are commonplace. Although, yeah, the reason stated in the answer key is much more stronger and much more valid. Yeah, I admit defeat. Okay. Number 17. What gave you the essential information to decide that 3 and 4 were heterozygous? So we're looking at generation 2, 3, and 4. This and this. How are they heterozygous? Are they heterozygous? Okay, so yes, we already know that the trait is recessive. So yeah, this is the trait. This is normal. Let's make that assumption again. This one's small b, small b. This one's big B, big B. We have big B, big B, big B, big B. So yes, from here, even if I don't make a Punnett square anymore, it's obvious that all of the offsprings get the same genotype as their parents. Like legit 100%. But this one, in that scenario, let's try illustrating it. Hmm. 100%. Ah, something's wrong in this illustration. If the trait here is recessive, then all females are supposed to be carriers, right? This is awkward. But yes, for males, unaffected. For females, which is this, um, they are carriers. They are carriers because they have no shade. They are not carriers if they are shaded already, such as generation 3, female number 3, or person number 3, which is a female. So yes, technically this person is heterozygous. But for person 4, sorry, why is my iPad pencil not working? Is it not working? Dude. Sorry. Yeah. Person 4, where were we? I actually don't know what's the answer for number 17. Okay, so the reason is because both parents were heterozygous or carrier. I don't really get that because here it's already clear that they are not heterozygous. Or maybe yes, the male could be heterozygous. Let's try to make a Punnett square again. Just to see a potential consistency. So, sure, these two could go here, and these two could go there. I give up. But I'm pretty sure, I have a gut feeling that I'm this, I'm, sorry, I'm this close to getting the right answer. I mean, understanding it. I'm this close to explaining it correctly to you. It can't be said that I'm entirely wrong, but yeah, I hope it does the job. Number 18. This is an entirely different question, which is basically this, what you're seeing right now. So let's read the problem first. So brown eyes are a dominant eye color, allele, and blue eyes are recessive. So brown for capital B, small b, recessive. So, okay, so we have a woman, brown-eyed, Okay, I suppose she is heterozygous because the father, sorry, let's go with the mother first. The mother had brown eyes. The father has blue eyes. Mhm. The mother can also be heterozygous because either way, what's presented as the dominant trait is the brown eyes. So we're not sure yet about whether the mother is this one or this. Hmm. Let's test using Punnett squares again. So this is the female. Male is B, B. Okay. What if we try this one? I don't think that matters at this point because we still have a capital B small b anyways, which matches the offspring. And yeah, let's continue on. Mary is a brown-eyed man. So a suitor is here. Brown-eyed man whose parents are also brown-eyed. So both parents are brown-eyed. So I think the man is capital B, capital B. Both parents are brown-eyed. So that's the mom. That's the dad. And they have a son who is blue-eyed. Small b, small b. Okay, so we're instructed to draw a pedigree. Oops. I need an extra page. Punnett square first. So this is the female. This is the male suitor. Positive B, positive B, positive B, positive B. Positive B small b, positive B small b. Okay, that's not possible. There's a 0% chance of having an offspring who has blue eyes. A son who has blue eyes. Definitely not possible. What if the suitor, the male suitor, is capital B small b? There's a chance. As you can see here, yeah, there's a chance. But something has to be changed between the mom and dad of the suitor. Um, who knows? Maybe. Wait, never mind. What if we have this kind of combination? Yeah, it's possible. Either of these two could resemble this suitor. How close am I to the answer? Let's see the answer key. Yes, it makes sense. We've gotten to this conclusion because only through this setting, this Z settings, can we produce a son who is blue-eyed. But yeah, at this point, I don't think it really matters, like whether the suitor's parents are capital B, or small b, because those are possible. yeah, what matters is that we know that the daughter in the suitor cannot be both capital B, capital B. So both are carriers or heterozygous, they produce a homozygous child. This is another render of what was drawn. Should I still make another pedigree diagram on this? Well, technically this already is a pedigree diagram. The only difference is that instead of writing the shape, I wrote the symbol instead of the sex. So yeah, let's change that. Male is box. Female is circle. Male is box. Male is box. Male is box. This is one ugly pedigree diagram, but it should do it. This is what matters. So what are the possible genotypes? Oh yeah, I've been doing the Punnett squares the wrong way, but nevertheless, they still yield results that are the same, even if I wrote like Punnett squares with something like, for males we have XY, for females we have XX. So yeah, missed opportunity, unfortunately. Yes. Okay, what are the next pages for? Okay, they're basically re-answered. Whatever we did answer, I did try answering them again before the exam, so just to be very sure. Just to realize that pedigree diagrams didn't really have much to ask in the exam itself, which was kind of sad. I could have done better in other pointers to review. Okay, we're finished with the worksheet on pedigree analysis. Whatever I skipped probably will be placed in the next videos to come. The reason why I skipped these slides or pages is because I'm not sure how to I couldn't really remember exactly the sources where I got these pedigree diagrams from, because it's a lot better to answer with instructions compared to just looking at my solutions, which basically serve as my reviewers already. So yeah, thanks for watching. I'll see you in the next video. Hopefully in the next video it will be the last for everything that's covered in third quarter grade 12 STEM local program biology. I'll see you soon.